Okay, now we're at problem number 19. We are starting this set of examples that are trig substitution problems. And let's see how we proceed for this one. Now, trig substitution problems, it's imperative that you have a correct triangle drawn. And there's always two correct triangles, two and only two. Meaning you can exchange the opposite and the adjacent side and you would still have a valid triangle. The hypotenuse absolutely can only be one thing. Now, when you have a minus problem like this under the radical, the square root of the first term will be the hypotenuse, and then the square root of the second term, 4x squared, will be 2x, can go on either side, and then the radical then will go on the other side. Now, it really wouldn't hurt to check Pythagorean theorem before you move on to the next step, because these problems can get kind of involved, and the last thing you want to do is be working through something that's, since it's not a correct triangle, you're not doing the right problem, you're making things in a lot of cases much more difficult than need be. But this is a valid triangle, but I could switch the radical on the 2x. And you could even do that if you set it up one way and maybe your trig functions end up being something you don't like. Maybe if you want to get them, I think here it wouldn't matter too much. I think it would still be cosines and sines. It wouldn't matter. So I don't think switching them would accomplish that much. But let's say you had a problem that involved tangents and secants. And if you put it one way, you may get cotangents and cosecants. And you don't want, so say you don't want that because tangents and secants are usually easier to work with. You could switch the two opposite in the hypotenuse, adjacent, not the hypotenuse. But not here. I think it doesn't really matter which side you put these two on. It's probably about the same level of difficulty. So remember, everything in this triangle has to be represented. We always have to get x. See, notice there's no x in here other than the radical, but there's no x term by itself, but we always have to get x because dx is the derivative of x. So right off the bat, I can say that cosine is the radical over 1. I always want to compare the radical to wherever the constant term is. There'll always be a constant term. So adjacent over hypotenuse, so there's cosine of theta would be square root of 1 minus 4 squared. And sine of theta would be 2x over 1, which is 2x. And I'm doing that to solve for x. So that would make x 1/2 sine theta. Then the derivative of sine of theta, of course, is cos of theta. So if the radical then is cosine theta, and dx is 1/2 cosine theta, when you multiply those together, you get 1/2 cosine squared of d theta. Right here. And we saw that the section on trig integration, we have an identity for the cosine squared. Let's see if we still have that up here. Yes, 1 plus cosine of 2 times the angle plus 3. Plus 1 plus cosine of 2 times the angle, all divided by 2. All right, so it's 1 plus cosine 2 theta all over 2. So I just took that 2 on the bottom out with this 2 from this 1/2 to make 1/4 on the outside. And from here, it's not too bad. We end up with the antiderivative of 1, which will be theta. The antiderivative of cosine of theta will be 1/2 sine of 2 theta. And I'll talk about theta here in a second, but anytime you have this kind of problem where you have this double angle, you're going to have to convert it to a single angle. And the formula for that's on the trig sheet that I provide. The sine of 2 theta is 2 sine theta cos theta, but this 1/2 in front is going to kill the 2 that comes from the identity. So you just end up with sine theta cos theta. Because our triangle is built on theta, not 2 theta, so we have to have it as a single theta. So now we have the antiderivative. 1/4 theta plus sine theta cos theta. Really don't need the plus c to the final answer. So we have to convert this back into x. And theta, technically you have 6 possible answers that are acceptable. You know, in a multiple choice question, you should be able to identify which one it is. If you're writing this out by hand, really there's 6 possible answers. So, for example, if I chose this one, and usually the answers are chosen kind of on the most simplest looking terms. In other words, sine of theta is 2x. Therefore, that makes theta equal arc sine of 2x. It's like you're applying the inverse function to both sides to kill out the sine. So, but if you were wondering, could you have said theta would equal arc cosine of the square root of 1 minus 4x squared? Yes, that would be correct also. And then, of course, I'm not going to go through the other 4 trig functions to tell you all the other 4 answers. But yeah, it's 6 possible answers for theta. But usually we're looking, the simplest one is the one you'd see as an answer choice. And then you get sine of theta and cos of theta right off the triangle. Sine of theta we know is 2x. We already have it down here also. But if we didn't, 2x over 1, the radical over 1. So it's 1/4 arc sine of 2x plus 2x times the square root of 1 minus 4x squared. And then all that's plus c. It's okay if you leave that answer like that. In multiple choice form, they might already have the 1/4 distributed through there, but that's not too difficult. Let's jump down here to number 20. We have the square root x squared over the square root of 25 minus x squared. So whenever you have minus on the radical, that means that radical is going to go on one of the 2 short sides. So like I was saying earlier, you can choose either one. It'll be different when we have plus between the 2 terms, but this is true. So I could either put it on the adjacent or the opposite. And that means then the hypotenuse will be the square root of the first term, square root of 25, which is 5. And the other side will be the square root of x squared, which is x. And please check Pythagorean theorem before you move on. I mean, I can tell that I didn't write it out, but I know that this is right. It's one of the 2 correct versions of this triangle. But you really should consider doing it before you move on, because it doesn't take that long to do a squared plus b squared equals c squared to make sure it's right. All right, well, we know we have to get x. We have to get x to get dx. We will also need x because of x squared. And then the radical, of course, we need. So first thing I did here is I chose to say, okay, cosine of theta would equal the radical divided by 5. So therefore, bring the 5 over, so left out the step here, but this is all right. 5 cosine of theta then equals the square root of 25 minus x squared. Sine of theta would equal x over 5. Therefore, x equals 5 sine theta. And then we need dx, which is the derivative, will be 5 cos theta d theta. And let's come back over here to the integral. I replace x squared with 5 sine theta, so I have 5 sine theta squared. And then dx is 5 cos theta d theta. And then the radical on the bottom is 5 cos theta. So you see the 5 cos thetas cancel each other out. And that will give me just 25 sine squared on top. So I'll pull out the 25. And then I have to use the identity for sine squared, which is very similar to cosine squared. The only difference is whether you have a plus or minus in the middle here. This one, it's minus for sine squared, so we're using that identity right there, sine squared. Okay. So we have 1 minus cos 2 theta over 2. You can bring the 2 out like I did to make it 25 over 2. Antiderivative of 1 is theta. Antiderivative cos of 2 theta is 1/2 sine 2 theta. And just like the last problem, the identity will be 2 sine theta cos theta, but the 1/2 kills the 2. So you're just left with sine theta cos theta. So this problem was similar in form to the last problem. So theta, if you rewrite this as sine of theta back to x over 5, yeah, you can't say arc sine of 5. So the 5 has to go back over. So you end up with arc sine of x over 5 or sine inverse. And then, so it's sine times cosine. Sine's x over 5. Cosine's a radical over 5. So this answer's good right here. or you may have to distribute it possibly for a multiple choice question. And there we go. And I can't emphasize enough, sometimes students will always tell me that they watch me do class and watch me do these in videos and it look easy. You gotta make sure you can work it out for yourself. Even if you are following what I'm doing, it's not the same thing as actually writing out a problem and completing it yourself. All right, let's look at this next one, number 21. Square root of 9 minus x squared over x dx. Have a minus, so I have the radical again on the adjacent side, which means we have the square root of 9, which is 3, and then square root of x squared, which is x. Check Pythagorean theorem, but this is right. The x and the radical could switch. So the cosine of theta is the radical divided by 3, so therefore 3 cosine of theta is the radical. Sine of theta is x over 3, so 3 sine theta is x. Therefore, 3 cos theta d theta would be the derivative of x dx. And we've got the radical here will be 3 cos theta. Dx is also 3 cos theta, but with the d theta. And then x itself is 3 sine theta on the bottom. And that gives me cos squared divided by sine. Yeah, I could see where this would be a little tricky to integrate. That's the beauty of integration. Sometimes you have to kind of think about it. It's not overly complicated as far as the number of steps, but to like work this out. Yeah, if we had, for example, if we had sine squared on bottom, we had cosine on top, it would be U substitution. But here we have to do 1 minus sine squared and then break it up as 2 separate integrals. So we have 1 over sine, which is cosecant. We have sine squared over sine, which is sine. So obviously, when you're working these, that's why we have pencils and erasers, and if something's not going right, just try to change your thought process a little bit. But it can be a challenge, but it's kind of supposed to be a challenge. If it wasn't a challenge, then everybody could do it. So we end up with cosecant minus sine. Cosecant's should be on my formula sheet. With anything that has, or the integrals, like I mentioned this earlier in another problem, if they have, these right here. If the integrals have natural log in their function, they're on this sheet. But if they don't, the regular trig integrals, you're supposed to know those. For example, you would be required to know that the antiderivative of sec squared is tan, or the antiderivative of cosecant squared is negative cotangent. But anything that has natural log in the answer are provided on that sheet. So once you have that, we have so cosecant is negative natural log of cosecant plus cotangent. Of course, then the antiderivative of negative sine would be positive cosine. And I went ahead and distributed the 3. And then, so we get everything right off the triangle. We're set here. So it's negative 3 natural log cosecant of theta. Cosecant would be hypotenuse over opposite. So it'd be 3 over x. Cotangent would be adjacent over opposite. So it's 9 square root of 9 minus x squared over x. I guess, you could merge those together and write them as one fraction. Not mandatory, but a multiple choice answer does that. Now, in this case, though, of course, you don't distribute the negative 3 through the natural log. That is absolutely incorrect. But I guess you could merge that into one fraction inside because they have a common denominator and break it up into 2 different logs. That's unnecessary, but I'm just saying what you could do. Cosine of theta is the radical over 3, or actually there it is right there. 3 cos theta is the radical, so it's the square root of 9 minus x squared. And then our friend, the plus c, right there at the end. All right. So number 22, we have a 3/2 power. And sometimes I'll see students mess this up because they'll actually try to put 3/2 on the triangle, but that's absolutely not correct. You can only have square roots on a triangle, so to take care of the 3/2 is you'll just raise your trig function to the third power. So don't put something raised to the 3/2 on a triangle. And okay, so with that being said, let's move on down here and get things set up. We obviously need x, don't we? So tan of theta would equal x over root 5. So x equals square root of 5 root theta, which makes dx be square root of 5 sec squared theta d theta. And now I need the radical in terms of the constant. So secant of theta would equal the radical over the square root of 5. So you bring the square root of 5 over, you get this. Oh, one thing I'll mention here, this is our first one we've done with a plus for the square root. If it's a plus for the radical, it always goes on the hypotenuse. And then you have the freedom to choose the opposite, and the adjacent are going to be the square roots of each of the terms under the radical. So yes, I could have reversed the x and the square root of 5 if I wanted to. Don't have to, but I could have. But when it's plus, the radical's got to be on the hypotenuse. So we have, so let's piece all this together then. So dx is my numerator here. It'll be square root of 5 sec squared theta d theta. Then on the bottom, here's what I was talking about. So if the radical is square root of 5 sec theta, and you want to go from 1/2 power to 3/2 power, you have to cube it. Because if you take 1/2 raised to the third, property of exponents, we multiply. 1/2 times 3 would be 3/2. So that's what you do to get that 3, whether it's 3/2 or 5/2 or whatever it is, you raise it to that appropriate power, not on the triangle. So there it is. So there's the cube. That's what gets it to 3/2. So we simplify this, and you're going to have 3 square root of 5s. One of the square root of 5s will cancel, leaves 2 square root of 5s multiplied together, makes this a 5 right here. You have a sec squared on top, a sec cubed on bottom. That would leave you 1 over secant. And one thing about trig functions like this, you never integrate 1 over a trig function. That's you know, you'd have to have a trig function over a trig function to have any kind of substitution. I've seen students take 1 over sec theta and call it some sort of natural log or something, but that's absolutely incorrect. What you do is you always convert it to its reciprocal trig function. And that's true for even like higher powers, 1 over sec squared, 1 over sec cubed. You always bring it up. And actually in this case, it makes it super easy when you do that. 1 over secant is the same thing as cosine. So now we just have 1/5 cosine of theta d theta. So the antiderivative of cosine is sine. So you just have 1/5 sine theta. So we go to the triangle to get sine. See, we don't already have it here on the right because we didn't use sine and cosine for this one, but we get it right off the triangle. Sine is going to be opposite over hypotenuse. So it's x over the square root of x squared plus 5. And the 1/5 in front, and there it is. That takes care of that problem. Number 23. The square root of 9x squared minus 4 divided by x. So we have a radical, a negative under our radical between the two terms. So that means we put it on either the opposite or the adjacent side. I put it on the opposite side this time. So by doing that, whichever side I put it on, the hypotenuse was going to be the square root of that first term. Square root of 9x squared is 3x. Square root of 4 is 2. And we're set. So let's piece this together. course, I need x. So secant of theta would be hypotenuse over adjacent, so it's 3x over 2. That means x would equal 2/3 secant. So the derivative of secant, we need to know that. That's secant times tangent. So we have 2/3 sec10. That's our dx. Tan of theta would be opposite over adjacent. I'm trying to get the radical now involving the number, using the number. So opposite over adjacent. That gives me the radical over 2, so I'll bring the 2 over. So that means 2 tan theta would equal the square root of 9x squared minus 4. So let's put everything in there. So the radical will be 2 tan theta. Dx will be 2/3 sec theta tan theta. And then we have x on the bottom, which is 2/3 sec theta. So the sec thetas and the 2/3 also cancel. Those terms cancel. So we're left with 2 tan squared theta d theta. Now to evaluate this one, you have to convert tan squared into sec squared minus 1. And when you do that, it's not too difficult, as long as you then know that the antiderivative of sec squared becomes tangent. The antiderivative of 1 is theta. So the antiderivative is tangent tan theta, so tan theta we already have right over here, but we could have gone back to the triangle to get it. Square root of 9 x squared minus 4 over 2. And then theta, once again, we've talked about this, could be any one of the 6 trig functions. I just chose, since I had sec theta equals 3x over 2, I just chose theta then to be arc sec 3x over 2, or sec inverse, same thing. And you could distribute the 2 if you wanted to. Keep in mind, though, very important thing, that the 2 absolutely does not distribute through that parentheses where the 3x over 2 is. The 2 would kill the 2 on the bottom here, but then you would just be left with 2 arc sec theta 3x over 2. Number 24, we have 5 over x squared times the square root of 9x squared minus 1. So obviously the 5 we can just toss out of there. So the main thing is that we have a dx on top is the key. So I need the radical, since it has a minus, is on one of the 2 shorter sides. I'll put it in the opposite. So the hypotenuse will be the square root of 9x squared, which is 3x. And then the square root of 1 will be 1 on the short side. And here we go. So sec x will be hypotenuse over adjacent, so it's 3x over 1, which is just 3x. X equals 1/3 sec theta, which makes dx equals 1/3 sec theta tan theta d theta. And tan of theta would be the radical opposite over adjacent over 1. So tan of theta is square root of 9x squared minus 1. So let's put everything over here in the triangle. And so d theta is 1/3 sec theta tan theta. On the bottom, we have an x squared, so it would be 1/3 sec theta all squared. And then we have the radical, which is tan of theta. So we put that in there. Looks like we got a lot of things that cancel here. Let's see. The tans cancel. 1/3 sec theta cancels the square out of here, so you're still left with another 1/3 sec theta. So 5 divided by 1/3 is the same thing as 15. And then we're left with 1 over sec theta, which we just saw this a little recently, turns into cosine, because you can't have reciprocals there. And antiderivative of cosine is sine. And sine is the square root of 9x squared minus 1 over 3x. And then, actually, if you didn't cancel this, reduce it, that's fine. But you could reduce the 15 over 3 to make 5. So we have that 15 in front. And then plus 3. And let's see. That's the end of the trig substitution problems, I noticed that I think I need to revise this for future generations. I don't think I did this intentionally, but I noticed that there was only one of these problems that had a plus between the radical. That doesn't mean I love the minuses better or anything like that. I just didn't, okay, well, I'll have to maybe redo this and take a problem out later and put a new one in or something. There's nothing wrong with those problems, but it is disproportionate there to the plus radicals. So that takes care of the trig substitution block of problems. Okay, this next block of problems, 25 through 30, involve partial fractions. And you can see that the first two problems are only looking for the partial fraction decomposition, and then the next four will involve both the decomposition and then integrating the result from the decomposition. Which actually with partial fractions, a lot of times is the integration is not too difficult. It's the getting it decomposed properly, and because you're pretty much looking at only a handful of things here on the integrals. You have possibilities for natural log, a lot of those possibilities, basic, U substitution, power rule U substitutions, and arctans. Those are the most common. I think that's it, but I don't want to say for sure if there's something I'm missing there. But now that's assuming the functions are all like variables x. See, I didn't really cover this. I've done problems in the past, never put one on a test, but it's weird. Sometimes you could have partial fraction problems with trig functions. Maybe one day I'll put that back in the notes or something. I don't think I'd ever put it on a test, but you can have a certain situation, like if you get it to work out, but you can, yeah, it just depends on the type of problem. Say if you had, I can't really keep forgetting that I can't. Let's say if you had, I don't know, 7 over, let's say if that's cosine x, and that's 1 minus sine of x here. You could actually break that into an a and b. In other words, a over cos x, there's my trusty dx, and then a over cos x and b over 1 minus sine x, and integrate it that way. I'm not saying that would be much fun, but theoretically that would work. So, all right, but that's not your concern. I was only saying that because when I said that the integrals are only going to be power rule, natural log, arctan, I guess there are some exceptions to that, but not for variable x. So here was number 25 transformed over here. Now this one has a repeated linear. The x minus 1 squared is a repeated linear. That means you have to have a term with x minus 1 squared and an x minus 1. The order of the two doesn't matter. I could have put x minus 1 first, then x minus 1 squared. And then we have an x plus 3. And it did not matter. I have to have an a, b, and a c. It would not have mattered where a, b, and c were. Any of them would be fine. And you'll get the right number that you need as long as you do everything else correctly. So the first step is always multiplying by what's the denominator on the left side, because that's your least common multiple. That's always going to be your least common multiple. So you multiply both sides by that. So on the left side, you always have the numerator left. That's it. But the right side is a little more interesting. So you just kind of, if you need to, however you like to do this, if you need to really write it out, cancel the terms or do like I did, write at it. I just sort of looked at it visually and said, hey, okay, first one I got x minus 1 squared, cancels x minus 1 squared. I'm left with x plus 3, like so. And then for the b, I'll have an x minus 1 and then an x plus 3 left, because you'll take away one of the x minus 1s. And then for the c, you'll cancel the x plus 3 and be left with x minus 1 squared. All right. Let's see what we have here. Now this, let's pick some values. You can do it that way. There's another way I did it in my notes too. That there was another way to solve these. This one I chose to pick the values. That's probably as good as anything. So if I let x equal -3, you can see that will wipe out a and b because they both have an x plus 3, and just leave c. So if you plug in -3 on the left side in your calculator, you'll get 144. Put in -3 here. -3 minus 1 is -4. -4 squared is 16. And so you have 16c equals 144. Therefore, c equals 9. If I choose another x, such as 1, 1 is good because 1 wipes out b and c because they both have x minus 1 terms. Put in 1, I get -4 on the left side. I get 4a on the right side. So a would equal -1. And then now, the next one, I choose 0 for x. Now that doesn't really wipe anything out. It just makes it an easier number to work with. So I can just, I just use the value that a is -1, and then I know that c is 9, so I use them. That's a little weird how I wrote this. I'm not real happy about the way I wrote this, but it's right. But in the sense of trying to confuse people. You put in 0 there, you get -3. A is the -1 that I have in parentheses, and the 3 would be from the 0 plus 3. Since I'm not able to use a stylus on this particular computer, I don't want to try to change it. But see, I got it right here. Well, not right. I got it right there, too. It is 3 times -1. But visually, see, I have the 9 for the c, and then 0 minus 1 squared is +1. Just reverse them. So it should have been -1 on the outside and 3 on the inside. But mathematically, it's equivalent. So b's are unknown. Put in 0 is -1. 0 plus 3 is 3. -1 plus 3 is -3. And just kind of work out the arithmetic. -3 plus 9 is 6. Move the 6 over, you get -9 equals -3b. Therefore, b equals 3. So the order doesn't matter. But a, as far as you'll have the right value over the right denominator. So a is -1, so it's -1 over x minus 1 squared, plus 3 over x minus 1, plus 9 over x plus 3. So this was only asking for the decomposition. It was not looking for the integration, which actually this one would have had, first one would have been a power rule. The next two would have been natural log. All right, here's one that I didn't actually show the factoring, but the denominator needs to be factored. First thing you do is you pull an x out of there, and then you have x squared plus 2x minus 3, and that factors into x plus 3 and x minus 1. So that's how I came up with these three terms: x plus 3, and x minus 1 by factoring this down. That gives me an a b, a c, and any order a, b, c over any denominator, that will be fine. And first, so we multiply by the LCM on the left, so we clear out the denominator on the left. We're left with the numerator. And for this one, you get rid of the x, and you're basically, every one of these terms is going to have the other two denominators with it, because this is what they call distinct linear, no repeats or anything like that. And these are pretty easy. The distinct linears are pretty easy to solve for. So I put 0 in here, because you see 0 would wipe out the b and the c because they have an x, and then solve for a. So you get -9 on the left side equals 3 times -1. So -9 equals -3a, therefore a would be 3. And then put in -3 on the left side, you get 24 equals -3 right here times b, because -3 wipes out a and c. I forgot to mention that. Wipes out a and c. So it gives you negative 3b, and then negative 3 minus 1 is negative 4. And that would give you right here that 12b equals 24, therefore b equals 2. And the last one, put in 1, because 1 wipes out a and b, because they both have an x minus 1. Put in 1 here. On the left side, you'll have negative 4. And then the right, for this term, you'll have c times 1, which of course is just c. 1 plus 3 is 4. 4c equals negative 4. Therefore, c equals negative 1. So you'll end up with 3 over x, plus 2 over x plus 3, minus 1 over x minus 1. One thing to keep in mind, I'm sure you know this, but I'll mention it anyway, that the a, b, and c, all those values do not have to be integers. They can certainly be fractions. Now, I don't like for the fractions to get too bizarre, but you certainly can, look at my notes for that section. You can see that the fractions, I had plenty of them that had fractions in there. Now, starting with 27 here, we're going to start integrating these. See, so we're going to do the decomposition, then we're going to integrate it. So this one has what the term we call irreducible quadratic. That means you have this 4x squared plus 9 essentially means that if you were setting it equal to 0, it would have imaginary solution. That's another way to look at it. But don't confuse that with 4x squared minus 9. Because if that was 4x squared minus 9, you would factor that into 2x minus 3 and 2x plus 3, and you would have distinct linear factors. Now this one, now you could have started with 4x squared plus 9, but since I started with the x first, I put a over x, and for that irreducible quadratic, you always have to put the next letter times x plus the next letter. So had I put 4x squared plus 9 first, it would have been ax plus b would have gone first, and then plus c over x would have been the right way. So bx plus c has to be. So even though we have 2 fractions, we still have 3 letters. All right, so we multiply by the LCM. We'll clear out the left side. And we're going to have a times 4x squared plus 9. And then we'll have bx plus c times x. And let's go from there. Now this one's sort of like I multiplied this one out and kind of used that grouping technique. If you want to go back and look at it more thoroughly in my notes, I didn't do it as thorough here. But anyway, if you distribute the a, you'll get 4ax squared plus 9a, and then you have bx squared plus cx. So what we're saying here is that if we have 4ax squared plus bx squared were to equal 20x squared, that's equivalent to saying that 4a plus b equals 20. You're essentially dropping the x squares. Now, since we have a cx here, and that's the only x term, and we have a 1x over here, obviously you don't see the coefficient, but you have cx equals 1x, therefore c would equal 1. And here we only have one constant term, 9a, so 9a would equal 45, therefore that means a would equal 5. And then, so now that we have a is 5, we can go back over here to 4a plus b equals 20. And if a is 5, 4 times 5 is 20 plus b, so b would have to be 0. And that can happen in these problems. When you have like a bx plus c, you won't lose unless it's a repeated quadratic. I don't put those on a test, but bx plus c, you could lose one of those two, but not both. So you see, we did lose one of those terms. That doesn't mean you will. Oftentimes you'll have still a number for b and a number for c. But the fact that we got b equals 0 here is not that big a deal. So that's okay. So don't worry about if that happens. And so here we go. Let's get ready to integrate this. So we have a 5 over x is the first integral, and then now the bx is gone because b is 0, so we have c is 1. So we have 1 over 4x squared plus 9. 5 over x would just be 5 natural log of x, and 1 over 4x squared plus 9 works out to be arctangent. U would be 2 over x, du therefore is 2 dx, so that means we have to put a 1/2 out there. So the reason why we have 1 over 6 here is you have a 1/2 for the du when you adjust for that, and the arctan formula automatically has a 1 over a in it. So this 1 over 6 then is composed of 1/2 times 1/3. Well, there's your 1 over 6. All right, let's take a look at number 28. So we have a similar to the last one in the setup. We have a linear term and the irreducible quadratic term. So I chose to put the linear term first, which you don't have to, but I did. A over 1 minus x plus bx plus c over x squared plus 4. So I cleared out the denominator, which will leave me a times x squared plus 4 plus bx plus c over 1 times 1 minus x. Now, I chose to multiply this out. I guess one thing I could have done, even before multiplying it out, see, there's a couple ways you can go about this. If I had chose 1 for x here, that would have wiped out bx plus c, and I can solve for a. So I would have gotten 1 plus 4 is 5a, 2 plus 13 is 15, 5a equals 15, a equals 3. That's what I get right down here too. But you can always switch methods. You can start out by eliminating and solving for one of them, and then doing it the way I did the last problem. So you could always switch one form to the other. But here I multiplied it, ax squared plus 4a, and then I FOILed this to get this result right here. So if ax squared minus bx squared equals 2x squared, that implies that a minus b would have to equal 2. And I have a bx minus a cx, but I don't have an x on the other side. So that's pretty much just saying there's a 0x on the other side. So if bx minus cx equals nothing, that means b minus c would equal 0. So that tells me b would have to equal c. And the last one, I have a 4a plus c would be set equal to that constant 13. So 4a plus c equals 13 with b equals c. See, if you already would have solved for the a equals 3, you would have been already ahead of the game, I guess, because you put the 3 in right here. But anyway, however you go about this, so I set it up like this and just did an elimination, added them, the c's cancel, and there I got the a equals 3. So if a minus b equals 2 and a is 3, b would have to be 1. 3 minus 1 is 2. And then c automatically equals b, so c has to equal 1. So here's our decomposition right over here with the integral sign in front of it. So there it is. Let's see. So it looks like I did the work underneath, well, for the first one. Now, one thing you got to be careful about here is this will be a small mistake, but it's still a mistake, so you want to watch out for it. Because, it's easy to look at that and, go 1 minus x, and that's going to be natural log. And it is going to be natural log. But it's different than if it was x minus 1. Because the one thing you have to look for here is that even though this is 1 minus x, du is actually negative 1. So we have to adjust for that negative. So we just watch for that. So here, right down there, so you see there's that negative that's coming outside here. So yes, it's a natural log integral, but it's a negative 3 there. So it's negative 3 natural log of absolute value of 1 minus x. Now the middle one's u substitution. So if u equals x squared plus 4, du is 2x dx, so I have to adjust for 1/2. So the integral ends up being just du over u, and that is natural log. Okay. And the last one, 1 over, see what happens was, let me go back up here and explain this real quick. So you had 1x plus 1. Basically, you had x plus 1 over x squared plus 4. So we had to split them up into two separate integrals. And then the 1 over the x squared plus 4 is pretty much straight up arc tan. A would be 2, square root of 4. So you have 1 over 2, arc tan of x over 2. And there we have it. Number 29 is pretty easy. Kind of weird that I added this one in after those other ones. Simple, pretty as far as this kind of topic goes. You a over x over b over x plus 3. You'd have a times x plus 3 when you clear out the denominator, plus bx equals 3. So if you let x equal 0, solve for a, you'd have 3a equals 3, so a is 1. Let x equal negative 3, you have negative 3b equals 3, so b would be negative 1. So you have 1 over x dx plus negative 1 over x plus 3 dx integrals, both natural log. But see this, this time the u is x plus 3, so du is just 1 dx. We don't have to adjust for anything there. And so the first one's easy enough, natural log of x, and this will be minus natural log of x plus 3. So that one was surprisingly easy compared to the others. Probably should have had it first. Oh well. And number 30, another repeated linear. We have x plus 2 squared, so I have to have an x plus 2 squared term and an x plus 2. And then 1 minus x is in there again. That's kind of weird, 1 minus x another time. Clear out the denominator, so we have 9 left over here. We would have the x plus 2 squared goes away, so I have a times 1 minus x plus b times x plus 2 times 1 minus x. And then we would have c times x plus 2 squared. One minus x's will cancel. We have x plus 2 squared. And as far as solving this, I didn't expand this one out and group them by terms. Looks like I just chose to eliminate, which is fine. I mean, yeah, you could start it one way, then erase it and start it the other. I guess that would have been a FOIL here, and this would have been a FOIL. I mean, it wouldn't have been that bad, but this is probably easier. Because that way, if I let x equal negative 2, that wipes out b and c pretty quick, and I can solve for a. So I'd get 3a equals 9. That means a is 3. If I let x equals 1, so that would allow me to solve for c, because it's going to wipe out a and b. So 1 plus 2, 3 squared is 9. 9c equals 9. So c would be 1. And then I just chose an arbitrary value of 0. And that way I would plug in my a and my c. So if I put in 0 here, I have 1 minus 0, which is 1, times the a, which is 3, leaves me a 3. I would have 0 plus 2, 1 minus 0. That gives you 2, 2b. And then 0 plus 2 squared is 4. So I have 9 equals 3 plus 2b plus 4. 3 plus 4 is 7. 9 minus 7 then is 2. 2 equals 2b. Therefore, b would equal 1. And I made another note about that, negative to watch out for that. So I have 3 over x plus 2 squared integral, 1 over x plus 2, and then 1 over 1 minus x. Now look at these last two first, okay? The middle one's straight up natural log. And 1 over 1 minus x gives you a negative here, so it makes it negative natural log of 1 minus x. And now the first one, be careful, that's not natural log. It's only natural log once to the first power on bottom. Now I didn't show the work here, but just imagine if I had, it would have been the following. It would have been, u is x plus 2, so you would have been integrating u to the negative 2 power, which would give you, power rule would give you u to the negative 1 over negative 1. So that negative 1 on the bottom is what's changing that from positive 3 to negative 3. And then I could have left it as x plus 2 to the negative 1 up on top, or dropping it down to the bottom like I did here. Either way is fine. So in other words, negative 3 times x plus 2 to the negative 1 is also acceptable. So yeah, that one's just straight up. It is U substitution, but it's also known as the general power rule. So that's how we came about this part right here. So that takes care of this block of problems on partial fractions.